Sintering is the process of compacting and forming a solid mass of material by heat or pressure without melting it to the point of liquefaction. Sintering happens naturally in mineral deposits or as a manufacturing process used with metals, ceramics, plastics, and other materials. The atoms in the materials diffuse across the boundaries of the particles, fusing the particles together and creating one solid piece. Because the sintering temperature does not have to reach the melting point of the material, sintering is often chosen as the shaping process for materials with extremely high melting points such as tungsten and molybdenum. The study of sintering in metallurgy powder-related processes is known as powder metallurgy. An example of sintering can be observed when ice cubes in a glass of water adhere to each other, which is driven by the temperature difference between the water and the ice. The word sinter comes from the Middle High German sinter, a cognate of English cinder. General sintering. Sintering is effective when the process reduces the porosity and enhances properties such as strength, electrical conductivity, translucency and thermal conductivity, yet, in other cases, it may be useful to increase its strength but keep its gas absorbency constant as in filters or catalysts. During the firing process, atomic diffusion drives powder surface elimination in different stages, starting from the formation of necks between powders to final elimination of small pores at the end of the process. The driving force for densification is the change in free energy from the decrease in surface area and lowering of the surface free energy by the replacement of solid-vapor interfaces. It forms new but lower energy solid-solid interfaces with a total decrease in free energy occurring on sintering 1 micrometer particles or 1 cal per gram. Decrease. On a microscopic scale, material transfer is affected by the change in pressure and differences in free energy across the curved surface. If the size of the particle is small, these effects become very large in magnitude. The change in energy is much higher when the radius of curvature is less than a few micrometers, which is one of the main reasons why much ceramic technology is based on the use of fine particle materials. For properties such as strength and conductivity, the bond area in relation to the particle size is the determining factor. The variables that can be controlled for any given material are the temperature and the initial grain size. Because the vapor pressure depends upon temperature, through time, the particle radius and the vapor pressure are proportional to 2/3 and to 1/3, respectively. The source of power for solid-state processes is the change in free or chemical potential energy between the neck and the surface of the particle. This energy creates a transfer of material through the fastest means possible. If transfer were to take place from the particle volume or the grain boundary between particles, then there would be particle reduction and pore destruction. The pore elimination occurs faster for a trial with many pores of uniform size and higher porosity where the boundary diffusion distance is smaller. For the latter portions of the process, boundary and lattice diffusion from the boundary become important. Control of temperature is very important to the sintering process, since grain boundary diffusion and volume diffusion rely heavily upon temperature, the size and distribution of particles of the material's composition, and often the sintering environment to be controlled. Ceramic sintering. Sintering is part of the firing process used in the manufacture of pottery and other ceramic objects. These objects are made from substances such as glass, alumina, zirconia, silica, magnesia, lime, beryllium oxide, and ferric oxide. Some ceramic raw materials have a lower affinity for water and a lower plasticity index than clay, requiring organic additives in the stages before sintering. The general procedure of creating ceramic objects via sintering of powders includes mixing water, binder, deflocculant, and unfired ceramic powder to form a slurry, spray drying the slurry, putting the spray-dried powder into a mold and pressing it to form a green body, heating the green body at low temperature to burn off the binder, Sintering at a high temperature to fuse the ceramic particles together. All the characteristic temperatures associated with phase transformation, glass transitions, and melting points occurring during a sinterization cycle of a particular ceramics formulation can be easily obtained by observing the expansion temperature curves during optical dilatometer thermal analysis. In fact, sinterization is associated with a remarkable shrinkage of the material because glass phases flow once their transition temperature is reached, and start consolidating the powdery structure and considerably reducing the porosity of the material. There are two types of sintering, with pressure and without pressure. Pressureless sintering is possible with graded metal ceramic composites, with a nanoparticle sintering aid and bulk molding technology. A variant used for 3D shapes is called hot isostatic pressing, to allow efficient stacking of product in the furnace during sintering and prevent parts sticking together. Many manufacturers separate wire using ceramic powder separator sheets. These sheets are available in various materials such as alumina, zirconia and magnesia. They are additionally categorized by fine, medium and coarse particle sizes. By matching the material and particle size to the wire being sintered, surface damage and contamination can be reduced while maximizing furnace loading. Sintering of metallic powders. Most, if not all, metals can be sintered. This applies especially to pure metals produced in vacuum which suffer no surface contamination. Sintering under atmospheric pressure requires the use of a protective gas, quite often endothermic gas. Sintering, with subsequent reworking, can produce a great range of material properties. Changes in density, alloying, or heat treatments can alter the physical characteristics of various products. For instance, the Young's modulus N of sintered iron powders remains insensitive to sintering time, alloying, or particle size in the original powder, but depends upon the density of the final product, where D is the density, E is Young's modulus and D is the maximum density of iron. Sintering is static when a metal powder under certain external conditions may exhibit coalescence, and yet reverts to its normal behavior when such conditions are removed. In most cases, the density of a collection of grains increases as material flows into voids, causing a decrease in overall volume. Mass movements that occur during sintering consist of the reduction of total porosity by repacking, followed by material transport due to evaporation and condensation from diffusion. In the final stages, metal atoms move along crystal boundaries to the walls of internal pores, redistributing mass from the internal bulk of the object and smoothing pore walls. Surface tension is the driving force for this movement. A special form of sintering is liquid-state sintering, in which at least one but not all elements are in a liquid state. Liquid-state sintering is required for making cemented carbide or tungsten carbide. Sintered bronze in particular is frequently used as a material for bearings, since its porosity allows lubricants to flow through it or remain captured within it. Sintered copper may be used as a wicking structure in certain types of heat pipe construction, where the porosity allows a liquid agent to move through the porous material via capillary action. For materials that have high melting points such as molybdenum, tungsten, rhenium, tantalum, osmium and carbon, sintering is one of the few viable manufacturing processes. In these cases, very low porosity is desirable and can often be achieved. Sintered metal powder is used to make frangible shotgun shells called breaching rounds, as used by military and SWAT teams to quickly force entry into a locked room. These shotgun shells are designed to destroy door deadbolts, locks and hinges without risking lives by ricocheting or by flying on at lethal speed through the door. They work by destroying the object they hit and then dispersing into a relatively harmless powder. Sintered bronze and stainless steel are used as filter materials in applications requiring high temperature resistance while retaining the ability to regenerate the filter element. For example, sintered stainless steel elements are employed for filtering steam in food and pharmaceutical applications, and sintered bronze in aircraft hydraulic systems. Sintering of powders containing precious metals such as silver and gold is used to make small jewelry items. Particular advantages of the powder technology include very high levels of purity and uniformity in starting materials, preservation of purity, due to the simpler subsequent fabrication process that it makes possible, stabilization of the details of repetitive operations, by control of grain size during the input stages, absence of binding contact between segregated powder particles, or inclusions, as often occurs in melting processes. No deformation needed to produce directional elongation of grains. Capability to produce materials of controlled, uniform porosity. Capability to produce nearly net-shaped objects. Capability to produce materials which cannot be produced by any other technology. Capability to fabricate high-strength material like turbine blades. After sintering, the mechanical strength to handling becomes higher. The literature contains many references on sintering dissimilar materials to produce solid-phase compounds or solid melt mixtures at the processing stage. Almost any substance can be obtained in powder form, through either chemical, mechanical or physical processes. So basically any material can be obtained through sintering. When pure elements are sintered, the leftover powder is still pure, so it can be recycled. Disadvantages. Particular disadvantages of the powder technology include 100% sintered cannot be charged in a blast furnace. By sintering one cannot create uniform sizes. Plastic sintering. Plastic materials are formed by sintering for applications that require materials of specific porosity. Sintered plastic porous components are used in filtration and to control fluid and gas flows. Sintered plastics are used in applications requiring wicking properties, such as marking pen nibs. Sintered ultra-high molecular weight polyethylene materials are used as ski and snowboard base materials. The porous texture allows wax to be retained within the structure of the base material, thus providing a more durable wax coating. Liquid phase sintering. For materials which are difficult to sinter, a process called liquid phase sintering is commonly used. Materials for which liquid phase sintering is common are C3N4, WC, SiC, and more. Liquid phase sintering is the process of adding an additive to the powder which will melt before the matrix phase. The process of liquid phase sintering has 3 stages. Rearrangement. As the liquid melts, capillary action will pull the liquid into pores and also cause grains to rearrange into a more favorable packing arrangement. Solution precipitation. In areas where capillary pressures are high, atoms will preferentially go into solution and then precipitate in areas of lower chemical potential where particles are not close or in contact. This is called contact flattening. This densifies the system in a way similar to grain boundary diffusion in solid-state sintering. Ostwald ripening will also occur where smaller particles will go into solution preferentially and precipitate on larger particles, leading to densification. Final densification. Densification of solid skeletal network, liquid movement from efficiently packed regions into pores. For liquid phase sintering to be practical, the major phase should be at least slightly soluble in the liquid phase and the additive should melt before any major sintering of the solid particulate network occurs. Otherwise, rearrangement of grains will not occur. Liquid phase sintering was successfully applied to improve grain growth of thin semiconductor layers from nanoparticle precursor films. Electric current-assisted sintering. These techniques employ electric currents to drive or enhance sintering. English engineer A. G. Bloxham registered in 1906 the first patent on sintering powders using direct current in vacuum. The primary purpose of his inventions was the industrial-scale production of filaments for incandescent lamps by compacting tungsten or molybdenum particles. The applied current was particularly effective in reducing surface oxides that increased the emissivity of the filaments. In 1913, Weintraub and Rush patented a modified sintering method which combined electric current with pressure. The benefits of this method were proved for the sintering of refractory metals as well as conductive carbide or nitride powders. The starting boron-carbon or silicon-carbon powders were placed in an electrically insulating tube and compressed by two rods which also served as electrodes for the current. The estimated sintering temperature was 2000 degrees Celsius. In the United States, sintering was first patented by Duval-Dadrian in 1922. His three-step process aimed at producing heat-resistant blocks from such oxide materials as zirconia, thoria or tantalia. The steps were molding the powder, annealing it at about 2500 degrees Celsius to make it conducting, applying current pressure sintering as in the method by Weintraub and Rush. Sintering that uses an arc produced via a capacitance discharge to eliminate oxides before direct current heating was patented by G. F. Taylor in 1932. This originated sintering methods employing pulsed or alternating current, eventually superimposed to a direct current. Those techniques have been developed over many decades and summarized in more than 640 patents. Of these technologies, the most well-known is resistance sintering and spark plasma sintering, while electrosinter forging is the latest advancement in this field. Spark plasma sintering. In spark plasma sintering, external pressure and an electric field are applied simultaneously to enhance the densification of the metallic, ceramic powder compacts. This densification uses lower temperatures and shorter amount of time than typical sintering. For a number of years, it was speculated that the existence of sparks or plasma between particles could aid sintering. However, Holbert and co-workers systematically proved that the electric parameters used during spark plasma sintering make it unlikely. In light of this, the name spark plasma sintering has been rendered obsolete. Terms such as field-assisted sintering technique, electric field-assisted sintering, and direct current sintering have been implemented by the sintering community. Using a DC pulse as the electric current, spark plasma, spark impact pressure, Joule heating, and an electrical field diffusion effect would be created. Electrosinter forging. Electrosinter forging is an electric current-assisted sintering technology originated from capacitor discharge sintering. It is under use for the production of diamond metal matrix composites and under evaluation for the production of hard metals, nitinol and other metals and intermetallics. It is characterized by a very low sintering time, allowing machines to sinter at the same speed as a compaction press. Pressureless sintering. Pressureless sintering is the sintering of a powder compact without applied pressure. This avoids density variations in the final component, which occurs with more traditional hot pressing methods. The powder compact can be created by slip casting into a plaster mold. Then the final green compact can be machined if necessary to final shape before being heated to sinter.